Assassins, to another episode of the Dark Assassins podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. You know, one thing that sets apart junior developers from senior, principal, or whatever level up in the hierarchy you want to go is your ability to quickly debug issues. Now, debugging is a core skill that any developer needs to know because you will be doing it quite frequently. And the more you do it, the better you'll get at it. And let me tell you, you will be doing it a lot. It's not a matter of if you have to debug something, but when you will have to debug something, because it will inevitably come up. Because even the most of senior developer will introduce a bug into their code and thus have to debug said code. Now, there's a lot of different techniques that can aid in your debug process that can help you to not only identify but also fix the bug a lot faster. And we're going to get into some of those techniques as well as giving some examples as well. So stay tuned for that in this episode. But first, let's start off with our trivia question for the week. So the MD5 cryptographic hash algorithm was published in 1992 as a successor to the MD4 cryptographic hash algorithm, producing a 120-bit hash value, and it was designed by who? So who designed the MD5 cryptographic hash algorithm? And that is your trivia question for the week. So moving right along, let's get into this week's cybersecurity tip. This week's cybersecurity tip is to use passphrases rather than passwords. So, of course, the key difference here is passwords are typically a string of characters ranging from, a few characters to a lot of characters, and generally they contain, just numbers or letters, and strong passwords contain both numbers and letters, as well as, special symbols like the $ or the ampersand or exclamation mark, things like that, as well as using a combination of both uppercase and lowercase letters. And the reason why you want to do that, of course, is to make your password more complex, so it's 1, harder to guess, but 2, harder to brute force. And typically, the longer your password is, the more resilient it is to things like brute force attacks and being in some dictionary or rainbow table somewhere that attackers can use to more quickly identify what your password is. Now, passphrases, kind of in contrast, basically opt for the approach of longer is better, because passphrases aren't nearly as complex as passwords, which, as much as that is a downside, it's also a positive. Because the problem with passwords is, in order to create a very good, complex, and strong password, it's very hard to remember it. Now, if you're using something like a password manager, this isn't necessarily as big of an issue, but the issue with having a lot of complex passwords is remembering them. And because it's hard to remember them, a couple things happen. One is reuse, which of course is a horrible idea. And 2 is you change like one number or one letter between your different passwords. And while yes, it's still a very complex password, if a threat actor were to get access to that password and they end up changing numbers around, like the last number or something, they could guess your password fairly easily. So those are some of the main weak points of passwords and why passphrases are generally the better option, because especially if you can create a passphrase that has a bunch of random words that don't have any kind of correlation or link to one another. Because the sheer unpredictability of word combinations and length just adds to the complexity of passphrases and makes them more resilient to things like dictionary or Rainbow's table style attacks. Now, kind of as I touched on, one benefit to passphrases is they're a lot easier to remember than complex passwords with lots of numbers and special characters and such, and as well as uppercase and lowercase letters. Because if you just have to remember like 3 words for your password, I think it's a lot easier to say remember 3 English words or Spanish words or French words or whatever your language is. It's a lot easier to remember 3 words for your passphrase. Just for example, you could of course have it 4 words, 5 words, or however long you wanted to. But just having to remember words rather than all that sequence of letters and special characters and numbers is definitely a lot easier, of course, to memorize a couple words. Now, the key, though, is the randomness and uniqueness, kind of as I touched on. You shouldn't use words or phrases that are linked or somehow related to, say, the organization you're a part of or an organization in general. And here's a couple examples of that. So, a example passphrase could be Michael Jordan basketball. Now, on the surface, that's fairly decent. Michael Jordan basketball is a good length. It's over 20 characters, but all of those are linked together. So is a threat actor going to be able to guess it? I mean, if they kind of knew the general principle about it, it'd be fairly trivial to guess Michael Jordan basketball, of course, those all being linked together. So it's not nearly as secure as if you had, random words. Now, another example would be Explorer Fusion Mustang, which, to be honest, sounds fairly random, but if you worked for Ford or you are someone who enjoys Ford vehicles or is just a Ford enjoyer, I guess, I don't know. All of those, of course, are models of cars that Ford makes. Rest in peace, Fusion. So that wouldn't necessarily be the best passphrase either, because those are all linked to an organization. Now, a good example would be something like refrigerator engagement spacecraft, because none of those are really linked to each other at all and aren't related to any kind of organization. So 3 random words kind of combined together to make a passphrase. Now, you could make this even more complex by, potentially capitalizing some of those letters, swapping out some letters for numbers, like maybe swapping the E's for 3s or the O's for 0s, kind of things like that, kind of what people typically already do in passwords, just to add even more complexity to it. But another way to generate good complex passphrases is to use just random word generators. Now, there's plenty of them online, so you can go pick your favorite one. But one common thing with these random word generators is you can select how many random words you want to generate. So if you want a passphrase that has, say, 5 random words, you could just go to random word generator of your choice, select 5 for the number of words you want, and there you go. There's your passphrase. Who needs a password manager to generate your passwords for you when you can use one of the many random word generators out there? Now, of course, you still have to remember that passphrase, so it's not saying that password managers are obsolete, but it does make things at least a little bit easier. Now, in addition to, capitalizing some of the letters in your words or swapping some of the letters for numbers, you could also intentionally misspell one or more of the words, assuming you can still remember it, to add even further complexity. So this could, pose an advantage to someone who is horrendous at spelling words, because they could literally tell someone their password, or passphrase in this case, and they still wouldn't be able to log in because they spelled one of the words wrong, because the person creating the passphrase thought it was right, but apparently it wasn't, and the person trying to use said passphrase can't get in because of the person's terrible spelling. So for all of you out there like me that can't spell to save their lives, this could actually be where that skill comes in handy. So take that, English teachers. So for some context to kind of gain an understanding of what we're talking about when we're, talking about complexity of like passwords and such, some research done by SpecOpsSoft, which I'll have linked in the show notes. A passphrase comprised of just lowercase letters. So you didn't use any of the techniques like using an uppercase and lowercase letters, swapping out certain letters for numbers, that kind of a thing. You only use lowercase letters. A 21-character long passphrase is slightly more secure than a complex password made up of numbers, upper and lowercase letters, as well as special characters that's 15 characters long. Assuming, of course, the method you're using to try to crack the password is just by brute force. Because, of course, if you have the password or passphrase in a dictionary or a rainbow table, for instance, where it's essentially already pre-computed, so you don't have to do any brute forcing, it's instantaneous and you're done anyway. So kind of course, if you're unfamiliar with the idea of brute forcing passwords, just kind of as a recap, brute forcing is literally just hashing a ton of passwords over and over and over again until you get the hash of the hash you're looking for. So for instance, for simplicity's sake, if your hash was AFE, you would basically hash a bunch of passwords until the result was also AFE, in which case you found your password. Now, of course, no actual hash algorithm used to secure passwords would be that short, because that would be a very horrible cryptographic hash algorithm. So of course it would be much longer, but for simplicity's sake, that's essentially what you're doing. You're looking to see whatever hash you're looking to match. You're looking to keep generating hashes of passwords until you get the same hash. That's essentially what's going on. So if you're looking to improve your security with your passwords, maybe switch to using passphrases instead. And that is your cybersecurity tip for the week. Now, before we get into the nerdy things I got up to, I have to admit some of my weakness today. My responsible half was not strong enough to hold out until the reviews of the Mac Mini dropped, and I caved and pre-ordered one. Now, this was there was a couple of factors that played into the role here. Now, when I say I pre-ordered one, I'm kind of using that term very loosely, because as of the recording of this podcast, the arrival dates of pre-orders, at least the earliest arrival dates is tomorrow, or if you're listening on the day this episode goes out, yesterday. I only ordered like one day ahead of the earliest arrival date, so not a whole lot of pre-order, but also with the config that I was looking to potentially purchase, the one I was eyeing up, over the past week and a half, I was noticing that the order date or the arrival date kept slipping further and further, and we eventually got to the point where it was solidly in December, and I was like, okay, that's pretty rough. But then I saw the fact that there were some quote-unquote leaked Geekbench benchmarks. Now, I say that in quotes because they weren't really leaked benchmarks in any real sense of the word. Really, all it was reviewers who Apple sent review units to in order to, get reviews out, when the products actually go live. They were running, Geekbench benchmarks, which automatically get uploaded to Geekbench whenever you run them. So in order for them to have the various numbers for their reviews. So the fact that they were leaked is kind of just used to, I guess, make it seem, I don't know, more interesting. It's really just reviewers getting their hands on the devices early and running benchmarks, so it's not really leaked per se, although I guess you could technically say leaked because they officially aren't out yet, but, that's neither here nor there. But anyway, the numbers I was seeing for the M4 series of chips, it was just too good, and with the fact that the shipping dates kept slipping further and further to the right, I was like, ugh, yeah, okay, I'm just gonna cave. So I did pull the trigger. So it's still gonna be a while till I get my hands on the Mac Mini, but when I do, I will definitely be sure to keep you all informed about how fantastic it is. I'll definitely be sure to run some code compiling various benchmarks in that regard to compare it to some of the other Macs I have, and I can almost guarantee you that it will be blowing everything out of the water by a fairly significant margin. So I'm very excited for that, and I am very much looking forward to getting my hands on it. And with that, let's move into what nerdy stuff have I been up to this week. Now, to quote the Dos Equis guy, sort of, a very strong paraphrase, I don't always go on travel, but when I do, I run my backup script. Now, I think he said something at least a little in that range. Okay, not really. But I did run my backup script, and the reason why I'm actually bringing this up is not because it's notable, because it's a fairly common thing that occurs, but rather I actually made updates to it this time in order to make it better. Now, previously, when I would run my backup script, I would have to manually remove the oldest backup on the Xserve in order to make room for the new one. Gross, I know, a manual process, and someone like me doing it, I mean, it's basically hypocrisy and blasphemy, to be honest with you. I'm as much ashamed as you are probably hearing about it. But I decided to make amends to that and fix that and remove this manual process, and of course did it with Ansible because this whole backup script is essentially a collection of Ansible playbooks wrapped in a bash script just to kind of kick everything off. So if you know me well enough, of course, having this manual process could not stand. So I updated the Ansible playbook to basically check the Xserve to see if it needs to remove a backup, and if so, do it. So remove the oldest one before copying the new one over from the NAS in order to make sure that the Xserve doesn't run out of space. Now, the key thing to note, though, is it does actually do a check to make sure there's at least one backup still remaining. So if, for instance, I ran the script and it removed the oldest backup, and for some reason it failed or terminated early or something happened causing the backup not to actually copy, it wouldn't then delete the only then existing backup. So if there's one there, it won't delete, it won't touch anything. It will only remove the oldest backup if there's more than one of them. So that's basically just to preserve that I always at least have one backup copy. Now, as the data on my NAS grows from various things, from backing up computers, documents, virtual machines, all that stuff, there may come a time where, due to the storage limitations of the Xserve, this 2 copies thing might actually not be viable anymore, and I might have to drop it down to 1. But in any case, the Ansible playbook is equipped to handle that such use case and can easily be adapted to do so. So that was a pretty clutch addition. And then I did some video game updates for the Pokemon game I'm making, but nothing really too major. It was just some very minor stuff. I didn't have a whole lot of time to work on it. Did I think some minor bug fixes and fixed some warning messages, but probably the most notable thing I did was in the conventions markdown file. So I created which in all honesty is kind of pointless at this point in time because I'm the only one contributing to it. But since the goal of this project is to eventually completely open source it on GitHub, I wanted to have some kind of file for anyone looking to maybe make contributions in the future to be able to have kind of a complete list, or at least as complete as I could make it, of kind of the conventions that I'm following in terms of like styling, what the code looks like, how to name variables, like what casing should you use, where your curly braces should go, all that kind of good stuff. One issue with that, though, that was kind of nagging me for a while is one of the things in that conventions read markdown file is it has an example of how the Doxygen documentation should look for functions. And because as part of my automated build script, my CI/CD pipeline in GitLab, it runs Doxygen in order to generate all of my documentation for me. And as a part of that, it compiles in the markdown files that exist in the repository, that of course being the README and this conventions file. And because I labeled that section as C++, it would interpret the Doxygen documentation as actual Doxygen documentation and completely strip it out from the markdown file. So in the generated both PDF and Docker container web format of it, it would be completely gone. So it would read essentially, you shall have Doxygen style documentation as seen below, and then below there was literally nothing. So it looked pretty bad. It was something that was kind of irritating me for a while, but it was one of those like very low on the priority list type of deals. I'm sure everyone that's been a software developer for a while that's been working on a project has at least a few of those, either active or in the past, where there's some issue that's just kind of nagging at you, but it's very low on the priority list. But eventually you just kind of get to the point where you're like, okay, I'm just going to take care of this right now. So that's what I did. I got it sorted out. So now it's not perfect, but it's a lot better than what it was. As it displays in like the README enter like in GitLab, it looks fine. But on the actual Doxygen generated documentation, it has like the 3 backticks and then CPP and then the code and then the 3 backticks at the end. So it's not like, perfect, but it's a lot better than it was before since you can actually see the Doxygen example and it's still formatted like code. It's just not color coordinated like the rest of the code snippets in it. But I guess that's something I'll have to live with. Maybe at some point I might go back and try to see if I can't actually get it color-coded with the actual documentation in there. But again, that would be something very, very low on the priority list. But with that, let's get into this discussion on debugging. So I guess first, for those who aren't really software developers or don't really know what debugging is essentially just the process of trying to identify, analyze, or fix bugs or defects in software. So you'll often hear, when software updates get pushed, whether that's your iOS updates or Windows updates, you'll see in the actual description for the update, if you actually read them, it'll often refer to, fixes bugs, or includes bug fixes or something like that. And essentially those are various defects that have cropped up that weren't caught initially, that have then been fixed and then pushed to the user. So effective debugging can improve code quality, although we'll kind of get to that in a little bit, but also can reduce development time and prevent user-facing errors. So, of course, the more errors that or the less errors that a user can face, and thereby the more user-facing errors you can knock out ahead of time, the better the user experience will be, right? Because from the end user perspective, if you're using a piece of software and half the time it doesn't even work, and 70% of the time it doesn't do what you want it to do, you're probably not going to be very likely to continue using that software. But on the other hand, like if the software works flawlessly, it does everything that you want it to do, you're probably going to be a lot more likely to continue using it and maybe even recommending it to your friends, your family members, coworkers, etc. So from the developer perspective, the more thoroughly you can test, debug, and eliminate all the bugs you can before you ship it is definitely the ideal scenario. Now, I mentioned that it can improve code quality, but that's more of a possibility and not a sure thing, because debugging doesn't explicitly fix things like magic numbers or hard coding numbers into the code rather than using variables. With that said, though, if you do experience a bug somewhere, like you did have magic numbers and you found a bug where you didn't change one of said magic numbers, and for your debugging you actually ended up using variables rather than magic numbers, in that case it can improve the code quality. But again, it's not a guarantee that just because you debugged a bug and fixed it, that you improve the code quality. Because again, you could, in theory, fix a bug and actually worsen the code quality because you used a magic number for your bug fix. But that's neither here nor there. That's kind of a semantic thing. But some of the common challenges that you'll run into when debugging is bugs honestly vary widely in both scope and impact on the software as a whole, because a bug can be anything from a syntax error, like maybe you forgot a semicolon if you're programming in a language that uses semicolons, or you didn't tab appropriately if you're using Python, to more complex or logic flaws where you're writing the code and say you're making a calculator application and you type in a product, a calculation, say 3 times 2, and the result you get is 75. Of course, that is not correct, and that would be an example of a bug due to a potential logic flaw, right? And of course, that's just a very basic example. The more complex you get into functions and algorithms, these logic flaws can be potentially a lot harder to diagnose, but at the end of the day, they are still kind of more of a logic flaw. Now, if you and or your team take a long time to fix or find said bugs, this can cause things like delays to your releases, frustrated users, and potentially costly production issues. Because, for instance, if you can't effectively debug your bugs and get rid of them, your users are going to have to deal with those bugs for a lot longer than they may like to. So the quicker that you can resolve the bugs and get those updates pushed to the users, the better, for at least from the end user's perspective. So effective debugging is honestly a skill that improves with practice. It's not something that you're going to be able to master overnight, but a methodical approach and experience is kind of what helps you become better at debugging, because it's not about memorizing solutions, right? It's not like in math you can memorize your multiplication tables. That's not how debugging works. Debugging is more of kind of building up your toolbox of sorts and kind of adding various debug strategies to your toolbox and being able to identify what kind of bug you're encountering, and then be able to pull out which tool from your toolbox is best suited to kind of analyze and solve those bugs and fix them. So as we'll kind of see as we get through some of the examples a little later on, a lot of bugs share some very common traits or characteristics which a more experienced developer would be able to identify and then know either exactly which debug strategy to use or what the outright solution is to fix it if it's a more trivial bug. So kind of before you can even get into debugging, of course, you have to understand the code base and the code structure, because the better you can understand how a program is structured and where the various dependencies lie, the more efficient you'll be at debugging the program. Because if you're new to the code base, being able to effectively read the code is key, because the more thoroughly you can read the code, if you don't necessarily fully understand it yet, is going to definitely help you kind of not only get up to speed on the code base, but it'll help track the bug a lot quicker than just kind of scanning through aimlessly lines of code trying and hoping that it'll just randomly pop out at you, which granted sometimes does happen, but not always. But the better you can understand how the program is structured and what functions call what, kind of what the flow of the program is, the more easily you'll be able to trace where the bug may lie within kind of that path in order to more easily pinpoint it and identify which portion of the code contains the bug and then fix it. And it's not always at the function that caused the error or where your output looks wonky, because sometimes you might, have a print statement that prints out the result of a function, which is wrong, but that function inside of it calls like 2 or 3 different functions, and those functions also call like 1 or 2 other functions. So you kind of have this nesting of functions going on. So if you kind of know the flow of the code, you can more easily track down, okay, which of these functions is actually most likely to be the cause of the bug, and then you can more quickly identify what the actual issue is. Because to be honest, that is one thing that can be hard, especially for young developers to kind of tackle, is, they'll see the error output in like their console that it's pointing to this specific line with this specific function, and they're spending, a lot of time trying to figure out what in this function is actually the issue, because they see the function that, caused the issue, but everything looks right. Now, granted, I've been there. I've dealt with that pain, but it takes a more experienced developer to realize maybe it's not actually in this function. Maybe I have to go trace back through some of the other functions that got called in order to find the root cause of the issue. Now, if your code is well documented and your code base uses something like Doxygen, JavaDoc, Doxy, or something similar that can auto-generate documentation for your code base, that can be an invaluable resource to better understand both the architecture as well as the functions and the makeup of the overall code base. So once you kind of can understand what the code structure is, that's just, of course, one part of the battle, because the second part is you have to have a debugging environment set up. Because if you don't have any kind of debug tools or any kind of build tools or anything like that to build and test the software, your ability to debug the software is going to be a lot more challenging. Now, when it comes to debugging, it's best to ensure that you can catch as many bugs as possible, and the easiest way to do that is to ensure that the environment that you are debugging in is as similar to, if not outright mirroring, the production environment in which the software is going to be running. So, for instance, if you're trying to make sure that you catch all the bugs in your cross-platform Linux build, if you're just testing locally on, say, your Mac OS or even Windows machine, that's not going to cut it. Because if you've had any experience developing cross-platform, you'll quickly realize that you'll encounter an issue on one operating system that doesn't exist on other operating systems. One of the biggest culprits of this, for instance, is using system calls on Windows versus like Mac OS or Linux-based systems, because they tend to be different. So if you're not adequately testing your cross-platform code on the various platforms you're trying to build for, you're more likely to encounter and introduce bugs than if you were actively testing for those platforms. Now, a great way to kind of mitigate this and kind of resolve this issue is use a tool like either Docker or some kind of virtualization solution to create a virtual instance of your production environment so you can test how your program will perform. So, for instance, if you're running, if you're creating a server, for instance, and it's going to be running on a Linux system, you could create either a virtual machine of that system to test your code on, or you could spin up a Docker container to test it in, or something like that. Because what you don't want to be is you don't want to be the works on my machine guy, because nobody likes that guy. And understanding the environment in which the bug was found can help you more easily replicate it and thus fix it. Because as a developer, one thing that doesn't help at all is when someone comes to you and say the code doesn't work. Because one of the first questions you're going to ask is, you're like, okay, well, what's it doing that it's not supposed to? And you're trying to probe, for the what actually is the issue, what caused the issue, in order for you to be able to replicate said issue. And it's a lot easier to potentially replicate the issue if your environments are the same, because you're trying to reduce as many variables as possible, right? It's like when you're going through school and you were in science class, and one of the key things about experimentation is if you're trying to experiment with one variable, you only want one variable in play in order to identify its output and the effect that it has on the overall experiment, right? The more variables you introduce, the less likely you're going to be able to specifically identify what result the variable you wanted to change actually had, right? So the more variables you introduce, like having a different development or having a different environment set up, using a different operating system, running a different build of the software, things like this all can add variables into the equation, which of course you're trying to reduce. So having the same debug environment as your production environment can be a fantastic way to just reduce another one of those potential variables from the equation in order to more easily replicate the bug, and then you can more easily fix it once you can replicate it and see how the bug occurs and what's causing it and where in the code that might be occurring from. Another key component to a debug environment is the debug tools and debuggers, because now most IDEs these days, or integrated development environments, have some sort of built-in debugger into them, and some of them even come with their own debug tools as well. So IDEs like Xcode, Eclipse, and Visual Studio, for example, all have debuggers built directly into the IDE. So if you ever encounter an issue or something, you can essentially add breakpoints. You can use the debugger to debug your code, and they're generally pretty helpful, so you don't have to put in a bunch of print statements all throughout your code, or the good old reliable debugging. But if you're too cool to use IDEs and you're just like an Emacs guy or a Vim guy and you only code through the command line because you're just so cool, you could also use like language-specific or standalone debuggers like LLDB, GDB, or PDP if you're using Python. Now, I hope you got your bingo cards ready since I'm about to talk about memory safe and unsafe languages again. But if you are using a memory unsafe language like C or C++, using a memory analysis tool like Valgrind is also an essential tool to ensure that you don't have any memory errors or leaks, and also just overall testing the memory performance of your program. So once you have your debug environment set up, you understand the code base, now comes into some of the tools when it comes to debugging. The first one, of course, as we kind of already touched on, is the all reliable, the print statement. Now, using print statements to track variables in the program flow is definitely something that you can do and is kind of the go-to for a quick and dirty, simple debugging solution. But it's not necessarily the most ideal solution because at the end of the day, you don't want a bunch of print statements clogging up your program, and the more print statements you add, the more print statements you then have to remove once you actually get the code working like you intended to. And depending on where and how many print statements you added, that could be potentially a rather tedious and annoying process. So print statements are definitely a viable and valuable debugging tool, but it's not necessarily the one you should always be turning to. Now, another debugging tool is logging. Now, a lot of more like, I guess, polished isn't the right word, but a lot of software that's intended to at least run continuously and just kind of in general will have some sort of logging capability built into them to track things like errors, state changes, and things of this nature. And most logging solutions, including the logging library I developed, which is a shameless plug, I know, include various logging levels. So things like info messages, warning messages, error messages, and debug messages, just as an example. And the reason why this is kind of valuable and important is because it allows you to use essentially print statements to print out as much information as you want to, but you can specify at runtime what information you actually want to be outputted either to the console and or a file depending on how your logging solution is configured. So this can essentially allow you to selectively decide how much you want to actually get printed. So for instance, if you're trying to debug a specific issue, say in your server that you're writing, you can have the logging level set to debug, for instance, so it'll basically print out everything that you have in your logging system. But if, for instance, during the release time, you don't necessarily want your log file being flooded with every single little, log information, right? Because like in debug, when you're trying to debug something, it might be helpful to know when you enter a specific function that may be the cause of your issue, but when you're actually running the release build, you don't care about that, right? You don't necessarily need to know that, but it is helpful to know during debugging, which is why having those different log levels can be beneficial because you don't have to remove them like you do with print statements in order to clean up your output. You can just set the log level at runtime to be a higher level like info or, for instance, rather than debug. So another debugging tool that you can use is breakpoints. Now, breakpoints in your IDE and debugger, what those essentially allow you to do is pause the execution of the program in order to examine the program state at specific points. So this can allow you to do things like analyze what variables are currently set to and track where and when things are being set to more effectively track data without having to clog up your console with tons of print statements. So if you're using breakpoints, you can essentially check step by step what your variable is getting set to, what it changed from, things like that, without having to do print. The other thing that breakpoints can also allow you to do is to identify exactly where your program is running into an error and analyzing the state that it's in before it encounters that error to better gain a better understanding of why the error is occurring. So for instance, if you're running your program and it crashes at, say, line 132, right? you can set a breakpoint, right before that line to see what the state of all your variables are before you get to line 132 in order to figure out why your program might be crashing. Because, for instance, you might be expecting a variable to be set, but it isn't, or maybe it's set to something you weren't expecting it to be and you didn't account for it, and thus it crashed your program. So things like that can be where breakpoints can come into effect and be beneficial to help you better understand why your code might be crashing. And they can be beneficial without, of course, having to add a bunch of print statements into your code. So now that we kind of understand some of the debugging tools and we have our environment, the next thing is kind of understanding some of the strategies about how to go about this debugging now that we kind of have our tools and everything in our toolbox. So one thing to kind of, when you're thinking about debugging, you kind of have to think of this like a school science project, right? Like using the scientific method for your debugging. So treat your debugging like an experiment. Make a hypothesis, test it, observe the results, and then iterate on it. So for example, if you suspect there might be some kind of database connection issue between like your backend and the database, and you're thinking that it could be the connection string you're using is wrong, you could potentially test this by replacing it with a known good one in order to remove that variable to try to identify if that actually is indeed your issue. Another potential solution you can use is kind of what's known as the divide and conquer method. So essentially what this approach is isolating parts of the program in order to pinpoint the bug's location. Because what you don't necessarily want to do is try to fix everything at once. Because if your code potentially has a lot of bugs all happening at the same time, trying to fix all of them at once can, one, be very overwhelming, and you're probably not going to get very far, because if you can't establish that one bug is definitively fixed, you might try to fix some other ones and think the one that you actually fixed is still broken, and then you change it, and then it just makes matters worse. So don't try to fix everything at once. Focus on one bug at a time. Now, an example of this is if, for example, you have a function that's performing a sequence of calculations and it's not outputting the correct result. Rather than trying to fix all of the calculations at once, what you should do is take them, one by one and identify that you're actually calculating the right part, for that part. So, the first part of the calculation, make sure you're getting the correct result. If you're not, fix that calculation and then move on to the second calculation, and then so on and so forth until you get to the end in order to try to identify where your miscalculation is in order to fix it. The next one is the one the Arch Linux community likes to use, which, by the way, I use Arch. Read the freaking manual. So jokes aside, of course, sometimes your bug may actually stem from using the wrong function or not using the function correctly. Now, this is fairly common if you're using, say, an API or framework and didn't read the documentation thoroughly in order to understand what the function does or what it returns, or maybe what one of the parameters were supposed to be that you passed in and you passed in something else, and as a result you kind of got the wrong result. Now, I think most people, am definitely guilty of this, of not reading the documentation thoroughly enough and using the wrong function. I've definitely fell for it, so don't feel bad if it's happened to you. Now, one nice thing about this is if you're using an IDE, depending on the function in question, some IDEs have built-in tools to allow you to either jump directly to that function so you can look at it directly, or some IDEs also have the functionality where you can kind of do some sort of right click of sorts on the function itself, and it'll kind of bring up a mini documentation window, kind of displaying things like the description of what the function does, what parameters it takes in, and what those parameters do or mean, as well as kind of what the return value is. So those kind of things can also help you better identify what the function is doing and if you're actually using it correctly, because sometimes that could be, the cause of your issue. You're just not using the right right function, then if you switch to the correct function, your code works just as you intended it to. The next one is a binary search of sorts when it comes to debugging. Now, this is particularly helpful for large code bases where you essentially selectively disable or even comment out sections of the code in order to identify where the error occurs. So, for instance, if you're dealing with a unknown bug in a sequence of operations, you start essentially by testing the midpoint and then kind of narrowing down your search area to see, okay, so I comment out the second half of the code, all right, or the second half of this function. In the first half, does the bug occur? No, it doesn't. Okay, it's not in that half. Let me move to the second half. All right, okay, it's in the second half. All right, let me comment out, this portion of it. And you essentially kind of narrow the code down that way in order to more effectively try to find the bug. The next one, as we've touched on in a previous episode, and pretty much did, I think, the whole episode on it, or at least a large portion of it, is rubber duck debugging. Now, since we kind of already did a large portion of an episode on this, I'll try to keep this brief, but essentially the goal of rubber duck debugging is talking through your code with a rubber duck, ideally a rubber duck. Alternatively, in a pinch, you could use another person, but ideally you use a rubber duck to identify any kind of logical flaws in your code. And kind of the logic or the reasoning behind this is often when you verbalize the code and what it's actually doing, it helps you kind of pinpoint areas that don't make sense or reveal faulty assumptions you had. It's kind of like when you're trying to proofread like an essay, for example. If you're just kind of reading it silently to your head, your brain will often kind of like fill in gaps or issues in the words themselves, and you can overlook mistakes. But if you're forced to read it out loud, you'll often catch a lot more of those, kind of grammatical mistakes. So it's kind of a similar principle here with rubber duck debugging. The next one, which I find to be very useful, is backtracing or backtracking. So kind of the idea here is, especially if you have your code open in a debugger and you say run into an issue, you can do what's called a backtrace, where essentially the debugger will output, every kind of call that the stack made from your issue. So you can kind of trace back your error, like back up the stack through the various other functions to kind of see, potentially where this error originated from or propagated from. So, but another thing that also backtracking can be done in like code, for version control purposes, is you can, if you have good version control set up, like using Git, for example, you can essentially trace back through the version history to see when that bug got introduced in the first place. So you can, identify where it first appeared on a commit by commit basis. But on the topic of Git, once you identify where in the code the bug is actually coming from, you can use git blame on that file in order to see who was responsible for creating that bug. So if you find a bug in a code base you're working on and you want to see which developer was responsible for it, you can use git blame on that file to see who it was. Now, I don't recommend running git blame if you're the only developer on the code base, because I think you probably know who is to blame for that issue. I know on, for example, my Pokemon project, whenever I encounter a bug, there's no need to run git blame because I know exactly who the culprit behind that bug was, and I'm always looking right at them. So some more kind of advanced, so those are kind of some of the basic debugging tools and methodologies you can use. But then some kind of more, I guess, advanced methodologies, you could say. We kind of already touched on this first one, which is kind of memory profiling and performance profiling. So we kind of already touched on in the debug environment segment about using a tool like Valgrind to do memory analysis, check for memory leaks, inefficient memory usage, or memory errors. But there's also, tools for other languages too, like Memory Profiler for Python, for instance. And other tools like performance profilers, things like flame graphs, JProfiler, or Orbit, can help you analyze performance bottlenecks and spot inefficient code sections, which can help you improve performance and kind of optimize your code base when you are trying to get to that release portion. Now, of course, if you are running your code through a performance analyzer or profiler, you probably want to be running with a release build rather than a debug build, because if you're running with a debug build, you're probably going to find a lot of bottlenecks and inefficiencies just because you don't have any compiler optimizations. So if you can have those, or actually, I guess if you wanted to be really hard on yourself, you could run it in a debug mode to essentially ignore all compiler optimizations in order to make your code as optimal as possible in a debug state. So I guess there's, you could argue both ways, I guess. Another one is kind of static analysis tools. So I think probably one of the most known in this space is a tool called SonarQube. It's probably the most known, but there's, of course, others that are comparable as well. But essentially what this allows you to do is analyze code for syntax errors, vulnerability, as well as code quality issues before you even run the code, which makes it perfect to include in things like a CI/CD pipeline, so you can scan the code as part of the pipeline. And then if for whatever reason it fails, one of your checks, like maybe it finds a vulnerability or detects a quality issue or something like that, it can essentially auto-reject the code from moving on in the pipeline and thus not actually deploy it, which can be very beneficial if it detects some kind of vulnerability, for instance, because the last thing you want is to be pushing vulnerable code to production. Now, the other cool thing about it too is you can also use it as a plugin for a few different IDEs like Eclipse and VS Code, for example. And this last one I say with some hesitancy, which is using AI-powered tools. Now, I say this with hesitancy because just like going to Stack Overflow for all your solutions, you want to use this, I don't know about necessarily sparingly, but you want to be cautious when doing this. Now, AI debugging tools specifically, like using a tool like Copilot or ChatGPT or whatever your AI assistant of choice is, it's similar to rubber duck debugging in the sense that you can kind of ask your AI of choice to help you with your debugging process, but it's also different because unlike with rubber duck debugging, the AI will actually give you suggestions. So kind of the issue with that is sometimes the AI will lead you down rabbit holes that you either shouldn't be going down or are just completely in the wrong direction, but it can be helpful for understanding a cryptic error message. So if you kind of ran into some bug you've never seen before and the compiler or whatever spits out some weird error message you've never seen, it's very cryptic, you could, give that to an AI assistant to kind of help you. Maybe it'll explain to you better of what that error actually is, which might give you a better sense of where this issue might actually be in the code or what's causing it. Kind of as I mentioned, kind of the big caveat here is because AI tools will give you suggestions and whatnot. AI tools are not a replacement for having a strong, good debugging knowledge, because the more reliant you become on it, the more it kind of becomes like a crutch. And to be honest, what I've found is they're often wrong. I personally haven't had the best luck with using AI tools to generate code for me. Now, maybe I'm just a horrible prompt engineer, and I need to get good and get with the times and better that skill maybe. But for me, I always find whenever I ask it things, it gives me the wrong result. Now, granted, sometimes it's at least semi in the right direction, but like I said, sometimes it'll just go down a rabbit hole and get fixed on going down that rabbit hole, which is wrong. Now, one thing I will say is the more verbose you can be with these AI tools, the better. So if you know exactly what you're looking for it to do. You have an example, you know what you don't want it to do, and kind of give that negative of what it shouldn't be. That can help tailor your results to be better, because the more, unlike with, I guess, search engines, or maybe with search engines, kind of the more specific you can be and more niche you get, generally I think the better results you get. Like if you just ask some like generic prompt, you're going to get a very generic response that's may or may not actually be very beneficial. I guess the whole point of this is to use the AI debugging tools sparingly. You don't want to overly rely on them, because you want to actually have those good debug tools, in your back pocket. And kind of as we touched on, the only way you're going to get better at debugging is if you actually debug rather than just asking someone for the answers, right? Because that's of course one of the things that teachers always taught you at school of why cheating was bad. Because if you cheat, you're not actually going through the work and getting those reps to kind of understand the process. You're just copying down the answer and you're not learning. So let's go through some common debug scenarios and kind of what the solutions are. So one problem you'll probably run into is either null pointers or undefined variable errors. So one common error that can sometimes be run into is accessing null pointers or uninitialized variables. And these can range from being harmless to potentially catastrophic, depending on the situation. So for non-pointer variables, it's best practice to initialize them first when you define them in order to avoid this situation entirely. Because not all programming languages auto-initialize variables for you or guarantee that variables will be initialized when you create them. So it's always best practice if you're creating, say, a new integer to always assign it to something, whether that's -1, 0, or whatever you want it to be. As for pointers, though, it's always best to check if your pointer is null before you use it so you don't accidentally try to access a null value. So always make sure you access your pointer or check your pointer to see if it's null before you use it in order to avoid this. Now, you don't have to check it every time you want to call something. Generally, if you have a function that creates a pointer or deals with a pointer, you check it once and generally you're good, unless there's some logic in your function that has the potential to free said pointer, in which case you, of course, again want to check to make sure it's not null. Next, we have the off by 1 errors. Now, these are probably some of the most common errors you're going to run into when you're dealing with loops, and it's definitely, I think, something more common amongst younger developers. I know when I was first starting out programming, I frequently ran into these off by 1 errors. Every now and then I'll still run into them. But essentially what this is you don't actually, you overextend the bounds of what you're trying to do, right? So you're off by 1. The best example to avoid this is double checking your bounds when doing loops. So for example, if you're using a fixed size array, or I guess really any array that you have the size of it, the best way to ensure you don't go off by 1 is to start at 0, because any real programming language starts their indexes at 0 and then goes through the size, but it's essentially the size minus 1. So if you're doing a loop, you can either go to less than the size, or you can go to less than or equal the size minus 1, kind of depending on what your preference is, but always kind of ensuring that you're not going to, less than or equal to the size, because if you go less than or equal to the size and you started at 0, then you're going to go 1 further than the loop has, and you're going to run into issues. The next one is race conditions. Now, race conditions, if you haven't done any multi-threaded programming before, you've probably never encountered one. But once you kind of start getting into some more performance-oriented programming and get into multi-threaded programming, Race conditions are some of the most aggravating bugs to debug because of how unpredictable and inconsistent they are. Because sometimes your output is exactly what you expect it to be. Other times your output is one value, and other times your output is a completely different value. And then other times your program might just straight up crash. It can be very aggravating because your error is never consistent. Because in most cases, like the errors we've touched on previously, your error is always going to be the same every single time you run the program. But that's not true with a race condition, which is why they are so hard to debug. But generally, the main reason why these occur in the first place is because multiple threads are trying to access and or manipulate data at the same time. So if you have one thread that's, say, trying to read a variable while another thread is trying to write to that same variable, that is where you're going to run into a race condition, because it's essentially who gets there first as to what the value actually is. Now, the solution for this is to add things like locking mechanisms or atomic variables. So starting off, I guess, first with the locking mechanisms, that's one of the most common ways to solve this problem, at least historically speaking, was to use some kind of locking mechanism like a mutex lock at the critical sections of your code, or in other words, places where a variable gets touched by different threads at the same time, and multiple threads can access that one variable. So that would be a place where you'd want to have a mutex around that variable to ensure only one thread is accessing it at a time. The other possible solution is to use what's known as atomic variables for those variables that multiple threads may be potentially accessing at the same time. So essentially, using atomic variables allows for lockless concurrent operations, or in other words, you don't have to use mutex locks, for instance. So atomic types essentially ensure that any read or write operations synchronize as part of multi-threaded operations, or in other words, you don't have multiple threads accessing and overwriting the same variable and thus having a race condition. The main caveat with atomic variables, though, is they really only work with trivially copyable types. So, for example, your built-in types like your ints, your floats, your doubles, those kinds of things, those will work perfectly as atomic variables. But once you kind of get into the more custom classes and stuff, that's kind of where you get into it's not trivially copyable, and thus atomic variables won't really work for you, and you'll have to kind of fall back to the mutex solution. And the last one I kind of want to touch on here, since I know we're going a bit long here, is infinite loops. Again, infinite loops happen to the best of us. I have, had many infinite loops in my day. But again, I think they're probably a little more common with the younger developers. But like I said, I have probably had it's definitely a non-zero number of infinite loops that I've encountered within the past year at least, and definitely maybe even more frequently than that. But anyway, essentially what an infinite loop is, if you aren't aware, is when your base case or your exit criteria never occurs. So think of this as your while true statement, or for instance, you had a while loop that you're checking if a value is greater than something or less than something, but then you never actually increment or decrement that value within the loop. That is a perfect example of an infinite loop happening. Now, a debug strategy that you can use to fix this is set timeouts or limit the number of iterations in a loop during the development process, just to kind of ensure that you don't actually run into a infinite loop. But generally speaking, they're fairly easy to identify because you'll either, one, get no output at all, and when in reality you should be getting something, or you just get a spam of a bunch of output really, really fast in the terminal, and you realize, oh, I got an infinite loop going on here. So those are kind of some of the easy telltales that you have an infinite loop. And of course, the way to fix that is to just ensure that you have some kind of base criteria that's actually getting met, or your exit criteria is being met. So for instance, don't do while true unless you actually want the loop to run forever, or you have a defined statement in your while loop that will break out once your exit criteria is met. Or if you're doing a for loop, making sure that your bounds checking is correct, and you're not gonna do the probably the most classic with the for loop is when you're trying to, say, go backwards down an array, for instance. So you start at the size and try to go to 0, but then just out of habit at the end you do, say, like I++ rather than I-, and you end up creating an infinite loop. Another very common occurrence. So kind of I guess to kind of wrap up here, when it comes to good debugging habits and kind of the mindset you want to be in, it's kind of crucial to stay calm and methodical when dealing with bugs, because one thing you have to remember is bugs are a natural part of programming, and all of us software developers introduce bugs into code. It doesn't matter how long we've been writing code for, all of us are introducing bugs on probably a daily basis. But part of the debugging process is making sure that you stay calm during that process, which can lead to more productive debugging. And in this is where I say, do as I say, not as I do. Because one thing that I am horrible at is I'll get stuck on a bug and I'll essentially beat my head against a wall relentlessly until I can figure it out, which often is arguably not the best solution. Because ideally what you should be doing is, when you get stuck on a bug for a while, if you're trying different things and it's not working, the best thing you can honestly do is to take a break and walk away for a bit. And whether that's you go out for a walk and think about it, you go up to get a cup of coffee, or basically anything to get away from the code for a few minutes, to kind of give your mind a break and, refocus and help you kind of think about the problem. Because it's kind of like when you're, going back to writing essays, right? One thing that I was horrible at when writing essays was my grammar and spelling, of course, was atrocious. And one thing that helped, it didn't solve my issue, but one thing that helped was to essentially, write the essay, kind of proofread it, maybe once or twice, and then literally step aside, leave, and just walk away for a while, and then come back to it with fresh eyes. Because what I found was, after reading over, the essay over and over and over again, any kind of minor issues I had, my brain would essentially kind of just skip over and fill in what was supposed to be there. And then when I came back to it after not looking at it constantly for hours on end, I would be able to catch those, and those would stick out. And the same thing happens with debugging too. Is like, if you're constantly looking at the same code over and over and over again, you can kind of tend to overlook things that if you came back with fresh eyes, you might be able to catch. Because another thing I've noticed is sometimes I'll be, working on, some code, run into a bug, and I can't for the life of me figure it out. And then I'll, ask like a coworker or a friend or something, hey, can you look at this code and see if you can, find anything wrong with it? And they almost immediately can point out exactly what's wrong with it, and it makes me kind of feel like an idiot, because it was literally right there in front of me, but I was just, so hyper-focused on trying to fix this bug that I was completely overlooking things. So if you ever kind of find yourself in that state where you're getting really, aggravated and annoyed that you can't fix this bug, just stop, get up, walk away, and take a break from that for a while, and then come back, with fresh eyes, so you can help kind of refocus and to just kind of forget about it for a while, so you can come back kind of with a fresh mind and fresh eyes to look at it. The next key thing to become better at debugging is to learn from past bugs. Now, this can be anything from keeping a bug journal or a repository of past bugs, or just documenting the bugs you've encountered and their solutions in order to better spot patterns and recurring mistakes in order to fix bugs a lot faster. Because this kind of goes back to the idea of having good documentation, right? And one thing that's honestly one of the reasons why I started heavily documenting things in my home lab, like things like setting up and installing various things. Because one thing that I found is often when I would try to do these things, I would run into minor hiccups along the way. And then I would get annoyed because I didn't write it down. So when I tried to go and do the same thing again, I would run into that same issue, but I didn't remember what I did to fix it. And this kind of gets back to the it's a solved problem thing that we talked about, I think maybe on the past couple episodes. It makes your life a lot easier if you already have a documented solution for a solved problem of sorts. So when you run into it in the future, it makes solving it a lot easier because you've, of course, already solved it before. So for me, when I'm trying to debug, what I'll often find myself running into is similar bugs that I've ran into in the past. And if I remember back to, what the issue was, what caused it, and, have that documented knowledge of what the solution was, it makes fixing those bugs a lot faster and much more trivial. So those are kind of the one things I wanted to touch on. Now, I guess to wrap things up here, at the end of the day, debugging is not something you're going to learn over and master overnight. Debugging is definitely an opportunity for growth to become better as a developer, because debugging is not just about fixing code. It's about understanding the code better and becoming a more skilled developer. And whenever you encounter a bug, think back to previous bugs that you encountered in the past. And if it's similar to one of those, you can kind of more easily, you can then recall, what you did to go about fixing it in order to then fix this one a lot quicker. And if it's a bug you've never seen before, definitely be sure to make a note of it, what the bug is, how it came up, and then ultimately what you did to fix it, and all the various steps, in that process. Because another thing that I've also found, and why documenting bugs is also very important, is because if I'm trying to debug something for an extended period of time, if I'm not, keeping track of what I've tried during the debug process, I'll often find myself testing, the same thing that I already tried previously and essentially just spinning my wheels. So if you can document the process of, what you did to fix it, what you've already tried, it can help reduce the fact of you trying something that already didn't work. Now, I guess the caveat to that, though, is sometimes you'll encounter that where one time it didn't work and then you went off and tweaked some things elsewhere, and then you came back and tried the same fix again, and that time it miraculously worked because you changed something somewhere else. So it's not to say that it's a foolproof plan. If you write everything you tested down and never go back to the things that didn't work, you'll be golden. But generally, it's good to kind of keep track of that stuff to kind of see, what the inevitable solution ended up being. Now, of course, like everything, like every skill, practice, right? You're only going to get better at debugging if you continue practicing. And the only way you're going to continue practicing your debugging skills is if you keep debugging, and the best way to do that is to write more code. Now, kind of to fully bring this full circle, being able to effectively debug can not only save you time, but also reduce stress, because if you can debug effectively, removing those bugs, nothing feels better than getting a program to work like it should be. So fixing bugs is definitely a way to do that, and it can ultimately lead potentially to cleaner and more efficient code as well. And debugging is definitely a long-term investment, but it is definitely something you want to be investing in if you want to see yourself as, doing software development professionally, or just you enjoy doing it and you want to become better at it. So if you find a solution that's literally just a Control-C, Control-V fix from Stack Overflow or some AI assistant, that's not necessarily a bad thing, but what you need to make sure you're doing is taking time to understand why that fix you copied and pasted works and what's different from the bugged version rather than just copying and pasting, right? Because if you just copy and paste the solution, you're not actually learning anything. So if you do find yourself copying and pasting a solution, definitely take a few seconds or a few minutes to kind of read through that code and understand why what they're doing actually works and why what you previously had caused a bug. So those are some of the skills, tips, and tricks, to become better at debugging and debug more effectively. But before we wrap up and close out this episode, let's get back to our trivia question for the week. So the MD5 cryptographic hash algorithm was produced in 1992 as a successor to the MD4 cryptographic hash algorithm, producing a 128-bit hash value, and it was designed by who? So again, who designed the MD5 cryptographic hash algorithm? If you said Ronald Rivest, you are correct. So congratulations if you got this week's trivia question correct. And if you enjoyed this episode or you got anything out of it from this talk on debugging, definitely be sure to give it a rating and review and subscribe if you haven't done so already. And be sure to share it with friends, family members, fellow software developers and engineers who might, need some tips and tricks on debugging. And if you have any questions about this episode or if you have any comments or topics or ideas for future episodes, be sure to shoot me an email or leave a comment down below if you're on YouTube. But you can shoot me an email at contact@darkassassinsinc.com, and the link for that, of course, is down in the show notes below. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bool nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.